This is chapter 3, probability. We're going to start off by introducing several concepts here um, that aren't things that you have to know long term, but they're things that make the things you do need to know long term make more sense. Okay, and so these first two that we're going to talk about here, outcome and event, and to some extent sample space, um, are things that you won't be quizzed over specifically, but they're definitions that help the rest of the chapter make sense. So it's just an FY before we get started here. When we use the term outcome, we mean the specific results of an experiment. And what I mean by that is I'm going to use this example throughout this first slide about flipping a coin twice. When we flip a coin twice, an outcome being a specific result is as specific as possible. What did you get in? What order did you get it in? The specifics matter. So an example is flipping a coin twice and getting a heads on the first followed by a tail. So the outcome is not, I got one heads, I got one tails. That's not specific enough because that could happen in multiple orders. Okay, so when we say an outcome, we mean the specific result. The order matters. In this case, for example, we get a heads first and we get a tail. So the outcome is the specific result as opposed to when we use the term event, we say any combinations of outcomes that can be summarized together. So when we say an event, we say flipping a coin twice and getting one heads, one tails. So an event is combining the outcome of heads, tails along with tails, heads, and just summarizing into one phrase of, oh, I got one of each. Okay. And the reason that's important to differentiate is because we're going to use the term outcome, and I want to make sure you don't get it confused with event because they're very similar, right? When you think about flipping a coin X number of times, your brain thinks, okay, there's two ways I can think about this. I can think about the specific order that I got everything in, or I can think about just what was the net result of those, several many coin flips. If you're familiar with the terms, it's a permutation combination idea. If you're not, that's fine. Don't stress about those two terms. But if you've heard those terms before, it's that idea. Okay, we just have to make sure we don't get them confused. And when we define the sample space, we say the set of all possible outcomes of an experiment. So not the set of all possible events, the set of all possible outcomes. And that's why it's important to note the difference, because we will talk about the sample space on and off throughout this course. And so for my example, since we're going to carry this through, we flip the coin twice. The sample space is heads, 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 tails, tails, heads, tails, tails. So the sample space is all of the possible outcomes, and that's important, again, for what we're going to define later on. Okay, so when we say sample space set of all possible outcomes, again, the order matters. I'm defining event almost to say, hey, you know this, you're already thinking of this, but we don't want to think about that in this course. We will not talk about events going forward. So if you want to make a note to yourself there, my purpose of defining this is because I know your brain's already thinking that, but so I want to be able to name it, but we're not going to be using events. We're going to be using outcomes in this course. Relative frequency is the number of times an event occurs during an experiment divided by the number of trials conducted. Put a star by this one. This concept is going to come up over and over and over again in subtle ways, and so you need to be very comfortable with this. It's just how many times did something happen divided by how many times, did we try to make anything happen, right? I shot 10 free throws. How many of them did I make? I made 6. Okay, my relative frequency is 6 out of 10. It's a very, very simple concept. And you're listening to this right now and you're saying, yes, this is a very, very simple concept. But a lot of times we'll get in the middle of a problem and I'll give an example like that and we'll ask for what the relative frequency is. And people won't have an idea of what it is. And I don't know if you're overthinking it or what, but it just goes back to this basic concept. Anytime you see a setup where we've done an experiment a certain number of times and you have a certain number of times it succeeded and a certain number of times that it hasn't, your brain needs to go right to relative frequency. Okay. And if you've seen this course before, or you've seen parts of this course before, this idea is going to manifest itself in a sample proportion. Okay, so some of you are are thinking, making that link right now, you're like, yes, I understand that idea. And that's what we're going to do in a lot of problems when we're asked for the sample proportion. We're going to do this concept here. They're kind of synonymous. Your textbook will not talk about a sample proportion here because we're thinking of it in terms of probability, not in terms of a sample. But it's a synonymous idea if you want to make that note to yourself. It's just how many times did something happen divided by how many times could it have happened. Okay, and so that's relative frequency. And we're going to contrast this with probability, which is a long-term relative frequency of an outcome. And we are going to think of probability, again, if you've seen any statistics before, we're going to think of probability as a population proportion. So that's how we're going to contrast these ideas. A relative frequency is we took notice, I think, number of trials, that's like a sample, right? How many times did we try out something, and then how many times were we successful? So it's just successes divided by total number of trials. That concept's going to come up over and over again. Make sure you're aware of that. It's just successes over total number of trials. And then probability, however, is a long-term relative frequency. And what I mean by long-term is, now we're thinking about theory. And this is where we start to get a little weird in the course, because we're talking about something that doesn't necessarily exist. We're just talking about the theory of long-term. What if we were to do this an infinite number of times? And you say, well, we can't do something an infinite number of times. I'm totally with you. When we talk about probability, we're talking about a true value, a what if we knew the truth type value. And again, if you've seen this before, you're thinking population proportion. If you haven't, don't worry, we'll get there. But it's this idea that if I go out and I shoot 10 free throws and I make 6 of them, my relative frequency is 6 out of 10. But is that the probability that I make the next free throw? And you'd say, no, the probability that you make the next free throw is whatever your true skill level is, right? And that's when we talk about, like, what if we knew the truth? What if we knew the real probability there? And so we're saying it's this, like, if we had an all-knowing, way to say this is exactly how good you are. Oftentimes, because again, now you're sitting here going, this is impossible, we could never actually know that, we can take a relative frequency, and if we deem that it's long-term enough, we can say that that's close enough to call it a probability. Now, we'll talk about later on in the course maybe a little bit more of, how do you know if you can do that or not? For now, don't stress about that. Just think conceptually. If you have a small number of trials, that leads you to a relative frequency. It's like a sample, and it's how many times are we successful over how many trials we had. And then a probability being long-term, just think a lot of trials. And again, don't get stressed out. I'm not going to ask you what's a lot. I'm not going to ask you to differentiate this number. Is this number a relative frequency or a probability? I'm not going to ask you that. What I need you to understand is probability is a long-term. What if we had an infinite number of trials? Or what if we had a near infinite number, a really, really big number of trials that we felt really confident with? That's a probability. Relative frequency is just what comes from, I went out in the backyard and I shot some free throws, that sort of thing. Okay. Some concepts of probability. A probability of 0 means that the event is impossible. A probability of 1 would be the opposite of it. That means the event is certain to occur. All other probabilities have to lie between 0 and 1. And just some notation for us, because you're going to see this throughout the course, we denote the probability of event A happening as a capital letter P, open parentheses, and then event A. So this would be the probability that event A happens. Now, oftentimes we're going to have equals or inequalities inside of those probability statements later. We'll cover the difference. For now, we're just talking about event A, like what is the probability event A happens. Right now, event A would be you make it to class on time. Okay, so there's no equals, there's nothing, it's just A is defined as the whole thing. Probability you make it to class on time. Okay, we'll get more complicated as we move forward into chapter 4. So the rest of this is going to be a little bit more disjointed. It's more of a collection of terms that we've deemed important for you to know. So it's not going to flow necessarily very well. It's going to be, these two go together and these two go together, and this is a good term, that sort of thing. So it's going to have a lot less flow because what we decided to do with chapter 3 is say, what are all the really important things, and then let's kind of take out the rest, because probability is its own very confusing topic. So we wanted to just say, here are the high points of probability that you need to be successful with the later stuff. So it may not flow very well. I'm just throwing a bunch of terms at you and ideas, okay? So the first one here, or the next one here, is equally likely. Equally likely is just as it sounds. It's when each outcome of an experiment occurs with equal probability. Again, make sure we understand it's outcomes, not events. What we mean by that is if I flip a coin one time and a fair coin, it's equally likely to get heads and tails. Those are two things that have equal probability. And again, probability long term, right? This isn't about I flipped the coin 10 times, what did I get? It's about I know that in the long term, if I were to flip that coin an infinite number of times, half of them would be heads, half would be tails. It is not equally likely to get one heads and two heads when flipping a coin twice. So when I think about a more complex experiment, my experiment in the second bullet point is flipping a coin twice. My experiment in the first one is flipping it once. So in the second bullet point, if I'm flipping a coin twice and I were to think about events, and this is why I said we don't think about events. If we were thinking about events, I can't call the events equally likely. Why is that? Because it's not the same to get one heads as two heads. And if you want to dive down that rabbit hole, you can kind of figure out why, right? There's only one way to get two heads, it's heads, heads. But there's two ways to get one heads, it's heads, tails, or tails, heads, right? So it's twice as likely that you get one heads than two heads. That's why we don't look at events, right? So I'm just trying to hammer that point home. Now, my third bullet point, if we're thinking about outcomes, we can say it's equally likely to get heads, tails, and tails, heads. And again, that should make sense in your head. And if you wanted to work through the math, you would say it's 25% likely to get each, right? And I know that because I have equally likely outcomes. I know that it's 50-50 for each time I flip the coin. And so I know that heads, 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 tails, tails, heads, tails, tails are all equally likely. It's 25% of all of them. Now, I want to make an important distinction here. Every time you have an experiment, you will not necessarily have equally likely outcomes. It works with rolling a die. If I think about it's equally likely to get 1, 2, 3, 4, 5, 6. It works with randomly drawing cards out of a deck. It's equally likely to get any of the four suits, or it's equally likely to get any of the different numbers / face cards, right? It's equally likely when we're talking about heads, tails. Why is that? Because everything has the same probability. Again, think through what probability means. It's long-term odds, okay? If I'm talking about shooting free throws, now I almost assuredly don't have this equally likely property that I have with flipping a coin. Why is that? Well, when flipping a coin, right, half the time I'm going to get heads, half the time I'm going to get tails every time I do it. If I'm shooting free throws, I probably am not just as likely to make as miss. Maybe I am an exact 50% free throw shooter, but that's not very likely, okay? No pun intended. So we have this nice property if I know that each individual trial, as in one flipping of a coin, one rolling a die, one pulling a card, whatever, if each individual trial is equally likely because it has the same probability of happening each time, then all of the outcomes of any complex experiment become equally likely, right? So what if I flip a coin 4 times? Think about how many different options you have, right? You have heads, 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 tails, 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 heads, heads, tails, tails, et cetera, et cetera. And you would say all of them are equally likely. Why? Because each individual coin flip is equally likely, right? So you have this nice property with things like that, but you have to stop and think, is this a setup where everything has the same chance? It doesn't change, much with the problem other than if you have this property, it can help shortcut you to some easier math. Okay, and so that's why we're introducing it here, because it's going to come up later. We're going to say, oh, these are equally likely, so I can just instantly say everything has the same probability of happening. Next, we're going to talk about a complement. This is a term we're going to use often in this course, so definitely highlight this one. First off, how we denote it, we're going to denote it a prime, or if complement event B would be B prime. You probably don't need to write the prime down as like a super stressful thing. That's just an FYI. The biggest thing is knowing what it is. A complement is a set of all outcomes not in that event. And it has probability equal to 1 minus the probability of that initial event. So this is very important. I want to make sure we get this concept here. We have two things with complements. We have what is the complement, and we have what is the probability of the complement. And this is where you may want to rewatch this video twice because, again, probability gets wonky. All right, it gets complex, especially if you haven't seen it. It is its own language for sure. We have an event A, you make it to class on time. The complement of event A is just the set of words that isn't A. It's everything that's not A. So the complement of you making it to class on time is you don't make it to class on time. Okay, so we have to be able to A, define what the complement is, and then B, we have to be able to talk about its probability. You need to be able to do both very well, very quickly, or else you're going to struggle later. Okay, and so when we say what is its probability, if A is you making it to class on time, and the probability of event A is 0.9, or 90%, will work in both decimal percent, doesn't really matter. Same thing, we can go back and forth, right? If the probability of event A is 0.9, the probability of making it to class is 0.9, then I would say, what is the probability of the complement of A? What's the probability you don't make it to class on time? It's just 1 minus that, so that's 0.1 or 10%. Okay, so very important concept there. Make sure you understand that very well. We're going to use that a lot throughout the class. Next, we're going to talk about conditional probability. Conditional probability is just in the English sense of the word, what is the probability of something conditioned on something has already happened? It's conditioning that something has happened. That's where the term came from. So the conditional probability of A given B, how it's denoted, the given is this vertical line right here. So probability of A, as you see right here, given that B has happened, it's the probability that event A will occur given that B has already occurred.